Hello and welcome to this revision session for AQA A-Level Physics on the topic of magnetic fields, which is part of AQA Paper 2. So what we're going to be looking at in this revision session is looking at how to answer A-Level Physics examination style questions, assessing your understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the questions in the revision session. When doing this, make sure to write in full sentences and show your full working out. Now on the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for AQA A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, student prep notes and the textbook to learn the key ideas of the course. Then secondly, test yourself. Use things like Caboodle, Seneca, the Student Knowledge Checker to quickly test your own knowledge. Finally, practice exam style questions. Use exam prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. So the three steps of learn the key facts, testing yourself and practicing exam style questions are how you should be revising for A-Level Physics. So what are the key facts to do with magnetic fields? Well, firstly, for magnetic flux density, the force on a wire in a magnetic field is equal to F equal BIL when the field is perpendicular to the current. We use Fleming's left-hand rule for the direction of the force on a current carrying wire. We define magnetic flux density B as the force per unit current per unit length on a wire in 90 degrees to the field. We also define the Tesla as the SI unit of magnetic flux density. In terms of moving charges in a magnetic field, the force on a moving charged particle in a magnetic field is F is equal to BQV, where the velocity is perpendicular to the field. Now we use the left-hand rule to determine the direction of the force and the movement for the positive charges, whilst we reverse the force direction if it is a negative charge. Now we know that charged particles can follow a circular path. That is when the centripetal force is due to the magnetic force, and applications which show this include things like cyclotrons and mass spectrometers. In terms of magnetic flux and flux linkage, magnetic flux is equal to phi, which is equal to BA, where the field is normal to the area. We know that the flux linkage is N phi for N turns of wire, and then when it's rotating a coil in a magnetic field, N phi, the flux linkage, is equal to BAN cos theta. Now we know for electromagnetic induction that Faraday's law is that the induced EMF is proportional to the rate of change of flux linkage, or EMF is equal to N delta phi over delta T. Lenz's law is that the induced EMF produces a current that opposes the change that causes it. Now for a straight conductor in a field, the EMF is induced when the conductor cuts through magnetic field lines. Now in terms of a rotating coil in a uniform field, the EMF is equal to BAN omega sine omega t, which is used in things such as generators, motors and induction heating. So let's have a look at a few questions to do with magnetic fields. So, why does a wire carrying a current experience a force when placed inside a permanent magnet? The current carrying wire is producing a magnetic field. The permanent magnet produces a magnetic field. The two fields interact to produce a resultant force on both objects. Why does a wire carrying a current produce a magnetic field? The wire is composed of charged particles. All the charged particles are moving and are producing a magnetic field. As there's a current flowing, the particles are all moving in the same direction, so the magnetic fields of each particle combine to produce an overall magnetic field for the wire. Why does a wire not produce a magnetic field when it is not carrying a current? The wire is composed of charged particles. All the charged particles are moving and producing a magnetic field. As there's not a current flowing, the particles are moving in random directions, so the magnetic fields of each particle cancels out. What is the relationship between the magnetic force produced on the wire and the length of the wire, and why? The length of the wire and the magnetic force produced are directly proportional. This is because the longer the wire, the more charged particles that the wire has, so the greater the magnetic force produced. There are more individual magnetic fields. This produces a greater interaction and a greater force within the permanent magnet. What is the relationship between the magnetic force produced on the wire and the current through the wire, and why? The current of the wire and the magnetic force produced are directly proportional. This is because the greater the current, the more charged particles that the wire has per volume, so the greater the magnetic field produced, as there's more individual magnetic fields. This produces a greater interaction and a greater force with the permanent magnet. What is the relationship between the magnetic force produced on the wire and the magnetic flux density of the wire, and why? The magnetic flux density of the wire and the magnetic force produced are directly proportional. This is because the greater the magnetic flux density, the more charged particles that the wire has per volume, so the greater magnetic field produced, as there are more individual magnetic fields. Again, this produces a greater interaction and greater force with the permanent magnet. What are the two conditions where a wire will not experience a magnetic force when inside the magnetic field of a permanent magnet? This occurs when the wire, and therefore the direction of current flow, is parallel to the magnetic field of the permanent magnet, and also when the wire does not have a current flowing through it. Why does a current carrying wire not experience a force when parallel to the magnetic field of a permanent magnet? When the wire, and therefore the direction of current flow, is parallel to the magnetic field of a permanent magnet, there is no interaction between the two fields. They are not crossing over each other as they're parallel to each other, so this means no field can be generated. Why does a current carrying wire experience a maximum force when perpendicular to the magnetic field of a permanent magnet? When the wire, and therefore the direction of current flow, is perpendicular to the magnetic field of the permanent magnet, there's a maximum interaction between the two fields as they're crossing over each other the most, so a maximum force is generated. How can the forces experienced by the permanent magnet and the current carrying wire be described? Which law of physics is this? So the two magnetic forces generated are of the same type, are of the same magnitude, act on different objects, and are in opposite directions. So this is Newton's third law of motion. What fields will this proton produce and interact with, and why? The proton is a charged particle, so it will produce and interact with an electric field. What fields will this proton produce and interact with, and why? This proton is a charged particle, so will produce and interact with an electrical field. As the proton is a moving charged particle, it will also produce and interact with a magnetic field. A proton is inside a uniform electrical field. Describe what will happen to the stationary proton here. It would accelerate uniformly in the direction of the field lines. How does the electrical field accelerate the proton? Why is this? The proton is accelerated by changing the speed of its motion. This happens as the motion of the particle is parallel to the electrical field lines. An electron is inside a uniform electric field. Describe what would happen to the stationary electron here, and why. It would accelerate uniformly in the opposite direction to the field lines. This is because the particle is negatively charged, and the field lines point in the direction of a positive charge. How does the electric field accelerate the electron, and why is this? The electron is accelerated by the changing the speed of its motion. This happens as the motion of the particle is parallel to the electrical field lines of the field. A stationary proton is inside a uniform magnetic field. Describe what would happen to the stationary proton here. The proton would not be affected by the magnetic field, as it doesn't produce or interact with a magnetic field unless it's moving. A moving proton is inside a uniform magnetic field. Describe what would happen to the moving proton here. Explain why this is. The proton will be accelerated in a circular or parabolic path downwards by the magnetic field. The proton would follow the path of the field lines as it is a positively charged particle. How does the magnetic field in this instance accelerate the proton? Why is this? The proton would be accelerated by changing the direction of its motion, as the magnetic field is at right angles to the direction of the motion of the particle. What type of force can the magnetic force be classified as in this situation? The magnetic force can be classified as the centripetal force, as the magnetic force acts at right angles to the motion of the charged particle. Why is the magnetic force always going to act as the centripetal force for the charged particle when it is in motion? The magnetic force will always be a centripetal force, as the theory of electromagnetism states that electrical and magnetic fields always act at right angles to each other, so the magnetic field will always be perpendicular to the motion of the charge. What is the relationship between the radius of the path and the mass of the particle in this instance, and why is this? Well, the radius of the curvature of the particle's path and the mass of the particle are directly proportional. This is because the greater the mass, the less the acceleration for the same force, as A equals F over m. This means that the particle does not deflect as much and the curvature increases. What is the relationship between the radius of the path and the velocity of the particle, and why? The radius of the curvature of the path and the mass of the particle are directly proportional. This is because the greater the velocity, the less the acceleration for the same force since it's travelling faster. This means the particle does not deflect as much and its curvature increases. What is the relationship between the radius of the path and the magnetic flux density of the field, and why? The radius of the curvature of the particle's path and the magnetic flux density of the field are inversely proportional. This is because the greater the magnetic flux density, the greater the force exerted on the particle, F equals BQV, so the greater the deflection on the particle and the radius of the curvature decreases. What is the relationship between the radius of the path and the charge of the particle, and why? Well, the radius of the curvature of the particle's path and the particle's charge are inversely proportional, because the greater the charge, the greater the force exerted on the particle, F equals BQV, so the greater the deflection of the particle, the radius of the curvature decreases. What is the relationship between the radius of the path and the specific charge of the particle, and why? The radius of curvature of the particle's path and the particle's specific charge are inversely proportional. This is because the greater the charge per kilogram, the greater the force exerted on the particle for its inertia. So the greater the deflection on the particle, and therefore the radius of the curvature will decrease. Charged particles can be accelerated by a particle accelerator. Why does the radius of the charged particle's circular path increase? The radius of curvature of the particle's path increases as the increase in the velocity will cause the radius to increase due to the equation r is equal to mv over bq. Why must an alternating voltage be used in a particle accelerator? The alternating voltage produces an alternating electrical field. This is to ensure that the charged particles are always experiencing an acceleration towards the other side of the accelerator and are therefore increasing in velocity and not decelerating. Why do charged particles spend the same time in a D in the accelerator even though they are increasing in velocity? The particles are moving with a greater radius of curvature when they're moving faster, so whilst they are moving faster they are covering a greater distance, so the time spent in the D remains fixed. What produces magnetic flux? What is it? The magnetic flux produced by a charged object in motion. The magnetic flux is the number of magnetic field lines passing through a given surface area. In which direction does magnetic flux point in? The magnetic flux of an object points in the direction that a positive charge would move in. Why is the magnetic flux passing through section A not the magnetic flux density? The magnetic flux density is the number of field lines that pass through 1 metre squared. Section A is only 0.75 metres squared. How could section A be altered to show the magnetic flux density of the magnet? Section A could be altered to be a region of 1 metre squared, then it would show the magnetic flux density of the magnet. How could section A be altered to show the magnetic flux linkage? Section A could be altered to be a conductor, as the magnetic flux linkage is the amount of magnetic flux interacting with a conductor. How do magnetic flux and magnetic flux linkage differ in their consideration of coils? Magnetic flux considers the magnetic field passing through a single coil or surface, whilst magnetic flux linkage takes into account the magnetic field passing through multiple coils, considering the collective effect of all the different turns. Can magnetic flux linkage be zero even if there's magnetic flux in individual coils? Yes, magnetic flux linkage can be zero if the coils are arranged in such a way that the magnetic flux through one coil cancels out the magnetic flux through another coil due to their orientations. What would happen to the value of the magnetic flux and flux linkage if the direction of the magnetic field changed? If the magnetic field changed direction, the magnitude of the magnetic flux and flux linkage would be constant but positive, and negative values would alternate as their vector quantities. Why is an EMF induced in a conductor that falls through a magnetic field? A falling conductor cuts through different magnetic flux as it falls. This gives a change in magnetic flux linkage. A change in magnetic flux linkage leads to an EMF being induced inside the conductor due to Faraday's law. When would an induced current be produced inside a falling conductor, and why? A falling conductor would have a current induced in it when it's part of a complete circuit, as a current can only follow inside a complete loop which has an EMF acting over it. What would happen to the size of the induced EMF in the conductor if the conductor moved faster, and why? Well, the size of the induced EMF will be larger, as there will be a greater rate of magnetic flux cut as the conductor fell. This would lead to a larger induced EMF due to Faraday's law. For a fixed conductor in a uniform magnetic field, how can the EMF be induced in the conductor? The induction of EMF in the conductor occurs when there is a change in magnetic field properties within or around the conductor. This change in magnetic flux induces an EMF and occurs when the current changes angle in the field as it alters magnetic flux linkage. For a spinning conductor in a magnetic field, when is the induced EMF the largest, and why is this? The size of the induced EMF will be the largest when the wire is parallel to the magnetic field lines, as the size of the magnetic flux linkage is low, but the change in magnetic flux linkage is high. The induced EMF is directly proportional to the change in magnetic flux linkage. It's Faraday's law. For a spinning conductor in a magnetic field, when is the induced EMF zero, and why is this? The size of the induced EMF will be zero when the wire is perpendicular to the magnetic field lines, as the size of the magnetic flux linkage is high, but the change in magnetic flux linkage is low. The induced EMF is directly proportional to the change in magnetic flux linkage. That's Faraday's law. So what is the relationship between the induced EMF in the conductor and the magnetic flux density of the magnetic field, and why? The size of the induced EMF and the magnetic flux density are directly proportional, as the greater the magnetic flux density, the greater the magnetic flux linkage for the same conductor, so the change in magnetic flux linkage will be greater as it rotates. What is the relationship between induced EMF in the conductor and the area of the conductor, and why? Well, the size of the induced EMF and the area of the conductor are directly proportional, as the greater the area of the conductor, the greater the magnetic flux linkage for the same flux density, so the change in magnetic flux linkage will be greater as it rotates. What is the relationship between the induced EMF in the conductor and the number of coils of the conductor, and why? Well, the size of the induced EMF and the number of coils of the conductor are directly proportional, as the greater the number of coils, the greater the magnetic flux linkage for the same flux density, so the change in magnetic flux linkage will be greater as it rotates. A spacecraft orbiting the Earth has a coil of wire in it. An astronaut measures a small current in the coil, although there is no battery connected to it and there are no magnets in the spacecraft. Why is this? As the spacecraft orbits the Earth, the magnetic flux linkage from the Earth's magnetic field through the coil changes as the angle in the magnetic field changes. The change in flux linkage induces an EMF in the coil, which as it's a complete circuit allows a current to flow in it. Wearing a metal bracelet in a region of a strong magnetic field could be dangerous. Why is this? As you and the bracelet move through the field, the magnetic flux linkage through the bracelet changes as the angle in the magnetic field changes. The change in flux linkage induces an EMF in the bracelet, which as part of a complete circuit allows a current to flow in it. This will cause the bracelet to heat up as electrical energy will be dissipated due to electrical resistance. Is it possible to induce a constant EMF for an infinite amount of time, and why? To maintain a constant EMF, there must be a continuous change in magnetic flux linkage. However, sustaining this change indefinitely is not practical due to factors like energy losses, resistance, and the dissipation of energy in forms of heat. In real-world applications like batteries or generators, they may provide a relatively constant EMF for a period, but the devices will eventually experience depletion, wear or tear, which will limit their ability to provide a constant EMF indefinitely. So, what happens to the movement of a falling conductor in a magnetic field and why? A falling conductor would slow down as there is an electrical current and magnetic field produced inside the conductor via Faraday's law that repels the motion of the conductor due to Lenz's law. This will cause the conductor to fall to the ground more slowly. Why is this an application of the conservation of energy? If the falling conductor produced an electrical current and magnetic field in the same direction as the motion, this would cause attraction. So this would cause the wire to fall faster, creating a larger current and magnetic field, producing a positive feedback cycle, which would mean infinite energy is produced. This cannot happen to the current produced, so therefore it must be opposing the motion of the conductor. What would happen to the motion of the conductor if it was made from a material of lower resistivity, and why? The falling conductor would fall slower, as for the same EMF produced in the conductor, a larger current will be produced, as there is less resistance. So there will be a stronger current and therefore a stronger magnetic field providing resistance, so the wire would fall slower. How could this principle be used in a braking system? If the braking disc was made out of metal and inside a magnetic field, the movement of the disc induces eddy currents in the metal disc in the presence of the magnetic field. This creates a force that opposes the motion of the disc, resulting in braking. What would happen if you pushed a conductor into a uniform magnetic field, and why? There will be resistance in pushing the conductor into the uniform magnetic field, as pushing the conductor into the magnetic field would induce a current and the magnetic field in the conductor, which would resist the motion of the conductor as it will be acting in the opposite direction to the motion. What would happen if you pushed a conductor into the uniform magnetic field faster, and why? There will be a greater resistance in pushing the conductor into the uniform magnetic field, as pushing the conductor faster into the magnetic field would induce a greater current and magnetic field in the conductor, which would resist the motion of the conductor more. So why does a traditional motor always have a top rotational speed? As the motor coil spins in the magnetic field, an induced current and therefore magnetic field are induced in the motor coil. Due to Lenz's law, these act in the opposite direction to motion, giving a resistance to motion. This dissipates energy from the motor and limits its top speed. What happens to the efficiency of a motor as you increase its rotational speed, and why? As the motor coil spins faster, the efficiency decreases. This is because the greater the spinning, the greater the change in magnetic flux linkage, the greater the opposing current, and the magnetic field would be in the motor, dissipating more energy from the system and decreasing its efficiency. So let's now have a look at some exam style questions to do with magnetic fields. A student investigates how the magnetic force on a straight current carrying wire depends on the strength of the magnetic field. The wire is suspended on a top pan balance as shown in the diagram. The wire lies at 90 degrees to the magnetic field between the two permanent magnets. The student varies the current and measures the change in the balance reading, which corresponds to the vertical magnetic force on the wire. The length of the wire in the magnetic field is 6 centimeters. The current in the wire is 3 amps and the measured magnetic force is 0.018 newtons. Calculate the magnetic flux density B. The student repeats the experiment with different values of current and plots a graph of magnetic force against current. Explain how the student can use the graph to determine the magnetic flux density and justify the shape of the graph. The teacher notes that the measured force is slightly greater when the wire heats up during the experiment. Evaluate how heating the wire could affect the measured force and actually the calculated magnetic flux density. So, pause the video now, then unpause the video when you want to go through your answer. In our first one, we know B is equal to F over IL. Pop in all the values and we get 0.10 Teslas. Now, as we know, F is proportional to I, so the graph will be a straight line graph through the origin. The gradient of the graph will be BL from looking at the equation. Now, since we know L, we can work out B as will be the gradient divided by L. Now, heating will increase the resistance of the wire, so the current may reduce for a given applied voltage. So if the current isn't measured accurately, the actual force will be measured to be less than what we expect. A technician investigates how the magnetic force on a straight wire depends on the properties of the wire and the conditions in which it is used. 4 different copper wires are placed perpendicular in the same uniform magnetic field. Each wire is connected in a circuit when the current and length of the wire in the field can be controlled. The table shows the recorded values. Determine if the magnetic field is uniform. Explain why each wire in the experiment experiences a force of different magnitude. The technician notices that when the current direction is reversed in wire B, the balance reading decreases rather than increases. Why is this? So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, we would use B is equal to F over IL to determine the value from each wire, and each wire will give B to be equal to 0.10 Teslas. This indicates that our field is uniform. Now the force varies because the current and the wire length differ between each test, so therefore a higher IL product gives a greater force for the same magnetic flux density. Finally, reversing the current direction in the wire reverses the direction of the magnetic force on the wire according to Fleming's left-hand rule. If the force was originally upwards, reversing the current makes the force downwards, so the wire pushes down harder on the balance. This results in a decrease in the measured mass when the force acted upward and an increase when the force acted downwards, hence the reversed change on the balance. A student investigates how the magnetic flux density inside a long solenoid varies with the current in the wire. The solenoid has 800 turns and is 0.40 meters long. The student uses a Hall probe to measure the magnetic flux density at the center of the solenoid for different values of current. The results are shown in the table. The student expects the magnetic flux density inside the solenoid to be directly proportional to the current. Use the data to evaluate whether the results support this expectation. The theoretical magnetic flux density inside a long solenoid is given by the equation B is equal to mu0 times by N times by I. Calculate the theoretical magnetic flux density when the current is 1 amp. Then suggest 2 reasons why the measured values of the magnetic flux density might be lower than the theoretical values. Pause the video now and then unpause the video when you want to go through your answer. Right, you would work out K for K is equal to B over I, and you can find out it's actually not constant. So when you do the different values, you'll find that they're given a different value for K. So this indicates there's not direct proportionality, especially at the higher currents. Firstly, we need to work out N, because N is actually the number of turns per unit length. So we would do 800 divided by 0.4, so it's actually 2000. We then pop in the values and we get 2.51 milliteslas. Now the Hall probe may not be perfectly calibrated or aligned. External magnetic fields, such as the Earth's magnetic field, may interfere with the results. And resistance in the wire may cause heating, which would affect the stability of the current produced. A beam of 3 particles, a proton, an alpha particle and an electron, enter a region of a uniform magnetic field at the same speed. The magnetic field is directed into the path and perpendicular to the initial velocity of the particles, that is moving to the right of the page. State and explain the direction of the force acting on each particle due to the magnetic field. Describe and compare the paths followed by the proton, alpha particle and electron in the magnetic field. Explain why the alpha particle follows a different path from the proton, even though both are positively charged and enter the field at the same speed. The student repeats the experiment with the same particles but doubles their speed before they enter the magnetic field. Predict and explain how the paths of the particles would change. So pause the video now and then unpause the video when you want to go through your answer. Firstly, the force on a moving charge in a magnetic field is given by the left-hand rule. So now the proton and the alpha particle experience a force upwards and the electron experiences a force downwards. Now the proton and alpha particle will curve in the same direction as they have the same sign of charge. The electrons curve in the opposite direction as they're negatively charged. Now the alpha particle has a larger radius of curvature than the proton due to its greater mass and charge. Now, finally, the alpha particle has a greater mass, it's 4 times that of the proton, and a greater charge, it's times 2. The increase in the mass has a greater effect than the increase in charge, as R is equal to mb over bq, so the alpha particle would therefore have a larger radius of curvature. Now finally, increasing the speed increases the radius of curvature. R is proportional to v, so double mv doubles the radius for all of the particles. A researcher sends charged particles into a region of uniform magnetic field directed into the page. The particles enter perpendicular to the field and follow circular paths. The table below shows data for 3 particles. Compare the motions of particles A, B and C. What conclusions can you draw about the effective charge and speed on the motion of the particle in the magnetic field? The researcher suggests that all particles are experiencing the same magnetic field strength. Comment if this is true. Some students incorrectly believe that a positive charge will always curve anti-clockwise in a magnetic field. Use this experiment to explain why this belief is incorrect. So pause the video now and then unpause the video when you want to go through your answer. Right, particles A and B have the same speed and radius but curve in opposite directions. This shows the direction of the curvature depends on the sign of the charge, not the speed. Now particle C has twice the speed of particle A and twice the radius. This suggests R is proportional to V when Q and B are constants. We know R is equal to mv over bq, so R is proportional to V over B for constant m and q. Now since A and C both have the same charge, and C's radius is double when the speed is double, B's must be the same too. Finally, particle A is positive and curves clockwise, but the direction of curvature depends on the relative direction of the velocity and field, as Fleming's left-hand rule. So the curvature is not always positive for anticlockwise or positive charges, it depends on the orientation of the magnetic field. A student builds a demonstration coil to investigate how EMF is induced when a coil rotates in a magnetic field. The coil consists of 25 rectangular loops, each of total area 3 times 10 to the minus 3 meters squared. However, due to the design and the setup, only 60% of the coil area lies within the uniform magnetic field. The coil rotates at a constant angular speed, omega is equal to 50 radians per second, in a field of flux density 0.20 teslas. The student is asked to determine the maximum EMF. Determine the correct maximum EMF that's induced in the coil. The student records the output EMF from the coil using a date logger connected to an oscilloscope. The EMF is found to vary with time as shown in the graph. Despite the setup being described as rotating uniformly, the peaks of the EMF curve appear slightly uneven, and the wavefront is not a perfect sine wave. Suggest two possible reasons for the observation and explain how each one could affect the shape of the waveform. The student claims that the induced EMF would be greater if the coil was rotated so that the plane of the coil is always parallel to the field. Evaluate this. So pause the video now, and then unpause the video when you want to go through your answer. Right, we know that the effective area is 60% of 3 times 10 to the minus 3, 1.8 times 10 to the minus 3. The maximum induced EMF is BAN omega. We pop in all the values and we get 0.45 volts. Now, this can be caused by a non-uniform rotation. Small variations in the angular speed will cause the EMF to fluctuate more rapidly and slowly at certain intervals, distorting the sinusoidal pattern. There may be an imperfect field. If the magnetic field strength varies slightly across the coil's motion, the EMF induced will not follow a clean sinusoidal shape. An uneven coil construction or partial contact with the field, which would change the effective area, would affect the flux linkage, causing inconsistent peak amplitudes. Now, parallel orientation means the maximum flux will pass through the coil, but the EMF is proportional to the rate of change of flux, not the maximum flux itself. Figure 7 shows a search coil position on the axis of an electromagnet, with the plane of the search coil perpendicular to the axis. A magnetic field is produced by a constant current in the electromagnet. Assume that the magnetic flux density inside the search coil is uniform. The distance between the search coil and the end of the electromagnet is x. Figure 8 shows how the magnetic flux density B of the field varies with x. The search coil has 200 turns and a cross-sectional area of 3.5 times 10 to the minus 5 meters squared. The search coil is now moved at a constant speed of 0.80 meters squared along the axis that x is increasing, and EMF is induced across the terminals of the search coil. Explain what happens to the value of EMF as the search coil moves. The search coil passes through the position where x is equal to 0.10 meters. Deduce whether the EMF will exceed 5 millivolts for values of x greater than 0.10 meters. So, pause the video now, and then unpause the video when you want to go through your answer. Right, to answer this question, what we're going to consider is the following. As the coil moves, there's going to be a rate of change of flux through the coil. The induced EMF is proportional to the rate of change of flux linkage, so the magnitude of the EMF will therefore decrease. Next, the gradient of the graph you can see is 0.69 teslas per meter. We can therefore use this to work out the EMF of the value by working it through, as you can see on the screen. So therefore you get a value of about 3.6 to 4.2 times 10 to the minus 3 volts. So the maximum EMF is the greatest at x is equal to 0.10, and you can tell this from the graph because at this point the gradient which links the EMF is the greatest at that point. Auroras occur above the Earth's pole when charged particles collide with gases in the upper atmosphere. These collisions produce tiny flashes that fill the sky with light, as shown. Collisions between electrons and oxygen atoms cause the emission of green light. And they calculate the velocity of the electrons that will cause green light of wavelength 560 nanometers to be emitted from an oxygen atom. Radio waves are also produced during an aurora. The electrons move in a circular path in the atmosphere emit radio waves. The frequency of the emitted radio waves is the same as the frequency of rotation of the electron. An electron with a speed of 1,650 km per second is moving perpendicular to a magnetic field, with magnetic flux density 48 microteslas. A radio station is broadcasting at a wavelength of 220 meters. Deduce whether the radiation emitted by the electron would interfere with the signal from the radio station. You should calculate the radius of the circular path of the electron. So, pause the video now, and then unpause the video when you want to go through your answer. Right, we know F is equal to C over lambda, so we can say 3 times 10 to the 8 over 560 times 10 to the minus 9. That gives us an F of 5.36 times 10 to the 14 Hertz. We know E is equal to HF, so E is equal to 3.55 times 10 to the minus 19 joules. This is all kinetic energy as it's moving, so V is equal to the square root of the 2 times the mass over the energy, so the energy over the mass, my apologies, so therefore it's 8.83 times 10 to the 5 meters per second. Next, we know that momentum is mass times by velocity, so it's 1.50 times 10 to the minus 24 kilogram meters per second. R is equal to mv over bq, so we work it out to be 0.196 meters. Lambda is equal to c over f, so therefore it's 224 meters. So we can see that the wavelength is about 220 meters. So this tells us, by the fact the radio station broadcasting at about 220 meters as well, the radiation emitted by the electron will cause interference with the radio station broadcast. Firstly, define magnetic flux. Then figure 4.1 shows a solenoid connected to a battery and the magnetic field through it when the switch S is closed. The battery has an EMF of 24 volts and negligible internal resistance. The solenoid is made from the copper wire. The wire has a radius of 4.6 times 10 to the minus 4 meters and a total length of 130 meters. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Calculate the current in the solenoid. Then a tiny electrical spark is created between the contacts of switch S as it is open. The spark is produced because an EMF is induced across the ends of the solenoid by the collapse of the magnetic flux linked with the solenoid. The initial magnetic flux density within the solenoid is 0.090 teslas and may be assumed to be uniform. The solenoid has 1,100 turns and a cross-sectional area of 1.3 times 10 to the minus 3 meters squared. The average EMF induced across the ends of the solenoid is 150 volts. Estimate the time taken for the magnetic flux to collapse to zero. So pause the video now, and then unpause the video when you want to go through your answer. Right, in our first question, we've got to be able to define what we mean by magnetic flux. Magnetic flux is the magnetic flux density times by the area normal to the field. We can work out the resistance as the resistance is equal to resistivity times by length over area, which because it's a wire is pi r squared. Pop in all the values and we get 3.32 ohms. The current is going to therefore be, when you're working it through, it's going to be equal to V over R. So therefore it's going to be 24 over R, which is 3.32, which is 7.2 amps. We know EMF is equal to the rate of change in magnetic flux linkage, so our initial value of flux is equal to 0.090 times by 1.3 times 10 to the minus 3, which is 1.17 times 10 to the minus 4. We can then say that the EMF produced is 150, so therefore we can work out our change in magnetic flux by doing the number of turns n times by the value we've just worked out over the time period. We can then rearrange it all and we get t to be equal to 8.6 times 10 to the minus 4 seconds. A solenoid is connected in series with a battery and a switch is illustrated. A small coil connected to a sensitive ammeter is situated near one end of the solenoid. As the current in the solenoid is switched on, there is a change in magnetic field inside the solenoid. State what is meant by a magnetic field. As the current in the solenoid is switched on, there is a current induced in the small coil. This induced current gives rise to a magnetic field in the small coil. State Lenz's law. Use Lenz's law to state and explain the direction of the magnetic field due to the induced current in the small coil. On figure 8.1, mark this direction with an arrow inside the small coil. The small coil has an area of cross-section 7 times 10 to the minus 4 meters squared and contains 75 turns of wire. A constant current in the solenoid produces a uniform magnetic flux of flux density 1.4 milliteslas throughout the small coil. The direction of the current in the solenoid is reversed in a time of 0.12 seconds. Calculate the average EMF induced in the small coil. So pause the video now and then unpause the video when you want to go through your answer. Right, so we know a magnetic field is a region where a force is exerted on a magnetic pole or a moving charge or a current carrying wire. The direction of the induced EMF or current tends to oppose the change that caused it, Lenz's law. Now we know that the magnetic field in the solenoid is increasing, so the field in the coil is in the opposite direction to oppose the increase. So the arrow should be just inside or above the small coil, pointing in the opposite direction to P. Finally, EMF is equal to the rate of change of magnetic flux linkage, so that's minus n delta phi over delta t. So you can pop in all the values from the question. Remember, we can work out phi by doing BAN to work it through that way, so you can work it out and we get minus 1.2 times 10 to the minus 3 volts. So, if we've been successful and we've learnt in today's revision session, we should be able to answer A-level physics exam style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So, thank you so much for watching this revision session on magnetic fields, which is part of AQA A-level physics paper 2. Thank you so much, and as always, have a lovely day.